Okay, so we're going to look at approximating the binomial distribution. So the book says that it can be difficult to calculate probabilities for x when n is large. Now, the main premise, this is for a binomial distribution, the main premise for that is quite simply the fact the book doesn't go, the tables don't go up beyond 50. And that's partially because to differentiate between the probability of, 40 occurrences when you're have 50 trials, or 50 occurrences when you've got 60 trials, the difference in the probability ends up being really so small, it's really quite difficult to tell the difference in a binomial distribution. But in some circumstances, we can use a normal distribution to approximate a binomial to actually calculate probabilities. But there are certain things that we need to consider for this to be the case. So, the conditions for which we can use a normal to approximate a binomial is when n is large, which should be when n is greater than 50, and when p is close to 0.5, because if the probability of success is really close to 0.5, then obviously it's going to be a more symmetrical distribution, because the likelihood of the occurrences between success and failure are almost similar, so therefore our curve should be equal on either side. So we can use a normal distribution to approximate a binomial in these cases. When this is the case, mu is equal to np, and sigma is equal to the root of np multiplied by 1 minus p. So these are the conditions for which these must be true. So we'll do an example together for this to be the case. So a biased coin has the probability of getting a head is 0.53, and the coin is tossed 100 times, and the number of heads x is recorded. Write down a binomial model. So x is binomially distributed with 100 trials and a probability of success of 0.53. Part B, explain why x can be approximated with a normal distribution of y is normally distributed with a mean mu and sigma for standard deviation. Well, we know it can because n is large and the probability of success, 0.53, is approximately 0.5. So I'd say for anything being close to 0.5, probably anything within 0.45 to 0.55 would be acceptable on that front. Is what I would assume they would probably do. Find the values of mu and sigma. Well, mu is 100 times 0.53, so it's 53. And sigma is the square root of np, which is 53, multiplied by 1 minus p, which is 0.47. So, do that on my calculator. Square root of 53 multiplied by 0.47 is 4.99 to 3 significant figures. Now, the problem with approximating a binomial approximating a binomial using a normal distribution is the fact that binomial data is discrete and the normal distribution is continuous. So I'm just going to show you part of the PowerPoint, which is taken directly from your book. So if you're using a normal approximation to a binomial distribution, you need to apply a continuity correction when calculating the probabilities. And that's because binomial can only take whole numbers, normal can take any numbers within the range. Now, it gives you 3 examples with no real explanation as to actually what the continuity correction is. And then it just expects you to be able to work it out. So to me, if I was looking at these examples and I didn't know any information about it, I would just think, well, if it's equal to, so like in this example, you obviously find the upper and lower bounds. But in both these examples, I would think, oh, in any other case, I've obviously got to round up. But that's not true. That's not the case. So I'm going to show you a table, which is really useful for you to figure out what the continuity correction is and for me to talk through exactly how it works using an example. So, got this table written out already. So, with anything for a binomial, when you do the normal, you've got to think of it in terms of lower and upper bounds. So, I want the probability in my binomial that x is equal to a. Well, let's say I wanted the probability that x is equal to 5 on my discrete random variable. Well, on my continuous variable, I could take anything from 4.5 to 5.5, and anything within that range would round to a discrete value of 5. So for my normal probability, I've got to take the probability of a subtract 0.5 to a plus 0.5. So you're finding the upper and lower bound of that case. For the probability that x is greater than or equal to a value a for my binomial. So again, if I want the probability that x is greater than or equal to 5. Well, for my normal distribution, that means I've got to take anything that is greater than or equal to 4.5. Or greater than, because there's no real difference in normal distribution, so it doesn't actually matter. Because anything 4.5, 4.6, 4.782 would all round to 5 were it to be rounded to the nearest whole number and to be written in discrete format. So that's the probability that x is greater than or equal to, though that side doesn't really matter, a minus 0.5. When x is just greater than a, so again, let's imagine now x is greater than 5. That means I do not want to include anything which could round to 5. So for my normal distribution y, it would have to be greater than the upper bound of that value, the upper bound of a. So the probability that x is greater than a plus 0.5. So the previous one was the lower bound. This one is using the upper bound. Now let's look at the less than. So the probability that x is less than or equal to a. So e.g. I want the probability that x is less than or equal to 5. Well, that means I want it to be less than anything that could round to 5. So, because I'm including anything which rounds to 5. So for my normal distribution, I need to use the upper bound, because I need to include that value a, because I want less than or equal to that value. So I need anything which could round to 5.5. Whereas if I just want the probability that it's less than 5, I need to look at the values that are less than the lower bound, because if I use, say, 4.6, 4.7, that would round up to 5, and I don't want to include those. So I'd have the probability that x is less than a minus 0.5. So I've put a, and this is the lower bound. So I've put a version of this table on my PowerPoint, and I've given you another example. Unfortunately, the example isn't in the same order, but obviously you can screenshot this video, pause this video to see my examples and my talking through it. But so that we can be clear with it, obviously let's do a couple of examples. So, a binomial random variable is binomially distributed with a sample size of 150 and a probability of success of 0.48. And this is approximated by the normal distribution, which we've called variable y, with a mean of 72 and a standard deviation of 6.12 squared. Use this approximation to find the probability that x is less than or equal to 70. So I need to approximate this as a normal distribution. So I need the probability that y is less than, well, I want the probability that x is less than or equal to 70. So I need to include anything that could equal 70. So I want less than the upper bound of 70, because I want it to include anything which could round to 70. So now I'm just using my calculator to do normal cumulative distribution, lower bound minus 1 times 10 to the power of 99, or whatever value you use, upper bound 70.5, mean, standard deviation first, 6.12, and then a mean of 72. So that's 0.403 to 3 significant figures. B, find the probability that x is greater than or equal to 80, but less than 90. So I need to deal with each end separately. So x is greater than or equal to 80. So I need to include anything which could round to 80, because I want anything that is more than or equal to 80. So I need to include anything which could round to 80, and because it's greater than, I need the lower bound to see what it would round up to there. On the other side, I've got x is less than 90. So I do not want anything which could round to 90, because I don't want to include 90. So I need 90's lower bound. So again, normal CD, lower bound 79.5, upper bound 89.5, which is 0.108 to 3 significant figures. So that's it, really straightforward in just a standard type question. For a question in context, for a particular type of flower bulb, 55% will produce yellow flowers. So our probability of success, which is going to be yellow flowers, is 0.55. A random sample of 80 bulbs is planted. Calculate the percentage error incurred when using a normal approximation to estimate the probability that there are exactly 50 yellow flowers. So let's just set up my binomial first. So x is binomially distributed with a sample size of 80 and a probability of success of 0.55. And I'm going to use my calculator to work out the exact value. So they've chosen a number that's small enough that your calculator can do it. If they didn't, then they'd be completely ruining the question. Okay, so on my calculator, distribution, I'm going to go to normal PD, because I'm finding a particular value. That's not what P stands for, but that's how I remember it. My cat's going to start meowing because the other cat's just come in, so I apologise that you're going to have meows in the background. Variable, so X is 50, N is 80, and my probability of success is 0.55. So the probability of getting 50 occurrences is 0.0365176. I'm going to use quite a few decimal places so that I can really get my accuracy level right for my percentage error. So I'm going to approximate this as a normal distribution. Now I need to work out mu and I need to work out sigma. So I'm just going to do them over here. So mu is NP, which is 80 times 0.55, which is 44, and sigma is the root of NP, which is 44, times by 1 minus P, which is 0.545. So the root of 44 times 0.45 is 4 points. Now, actually, I'm going to use my exact value because my calculator gave me an exact value. So 3 root 55 over 5. So to approximate this, I would be approximating the probability that y is between 49.5 and 50.5, because that is our lower and upper bound for 50. So I'm going to do this as inverse normal in my calculator. Not inverse normal, normal CD. So 49.5 is the lower bound, 50.5 is the upper bound. Standard deviation of 3 root 55 over 5. And mean of 44, which is 0.0361. Now I took 1, 2, 3, 4, 5, 6, 7 decimal places, so I'll take 7 decimal places here. 0.0361833. So to calculate percentage error, I need to find the difference between the exact value and the approximate value. So obviously difference meaning subtract and divide it by the original or the exact value. I want the modulus of that because it doesn't matter if it's positive or negative. It doesn't matter if it's an error above or below. You just want to know what the error is. And then times by 100. Can I remember how to find the absolute value? Yes. Shift absolute. 0.0365176. Subtract 0.0361833 over my exact value. I know that I've used rounded values, but the percentage error will be accurate enough to 3 significant figures by using that anyway. So the percentage error is 0.915% to 3 significant figures. So it's really not actually that inaccurate an approximation, within 1% of what the real value is, which shows that it is a good approximation and shows you that it was right to use it. And it is possible they would follow up that question with was it appropriate to use it? So you would say yes because n is large, yes because p is close to 0. It's only just, close to 0.5. It's only just what I would call within the range, but it is. And the percentage error is within 1%, so it shows that it is quite a good percentage error. So that is how you'd use it for approximating a binomial distribution. And just when I was going to film the cats, they have run away again. Sorry.